All right. Good evening. Can you all hear me? Okay, great. Yes, thank you very much. Jami, you raise your hand. Do you have any questions? Oh, okay. I believe you may say, yes, you can hear me, right? All right. Okay. So let's get started. It's 7 p.m. Before we discuss seminar 4, so let's go back to seminar 3. Maybe we have a quick review of what we learned in seminar 3. Okay, because there are a lot of stuff, right, in seminar 3. Okay, let me go to seminar 3. Yeah. Okay, quickly review what we learned in seminar 3. Okay. Yeah, basically in seminar 3, we are dealing with actually you can say non-stationary time series, right? So the time series have trend. The time series have cycles, seasonalities, and a random disturbance. So we want to see the maybe you can see the certain part of this time series. So some certain information from the time series. So if we look at the trend, because a time series can decompose into 4 components, right? The trend, the cycles, the seasonality, and the random parts, right? Random factor. And here, if we just look at the trend, so we can use a simple linear regression, right? Simple linear regression, and the regressor, or you can say the independent variable, are time. So if you look at the trend, if it is a linear trend, so the independent variable just the time. If the trend is, for example, quadratic, right? You have maybe additional term t squared as additional independent variable. And if it is a cubic, maybe even a very sharp increase or decrease, right? You can have maybe even t to the power of 3, okay? In your linear regression model. Okay, so seasonality. Okay, for seasonality, so you look at the data, whether your data have clear cycles with a certain period. Okay, sometimes it's not easy to differentiate between cycles and seasonality. So this is why in some textbooks that do not clearly differentiate between cycles and seasonality. Okay, so for seasonality, it is also a cycle. The thing is, the cycle has a clear period, right? So when you have, for example, in a season, in your data, you know the length of your seasons. Then you will include, for example, you have L seasons. You will have L minus one dummy variables, and then you use these dummy variables to create a simple linear regression function. Okay, and then to model the seasonality in your data. Okay, and then you have if you incorporate both trend and seasonality, right? So you have time as the independent variable, and also the seasonal indicators as independent variable in your multilinear regression model. Okay. Sometimes you might also have the multiplicative impact. For example, the seasonal impact and the trend have multiplicative impact on the time series. So you have joint terms of the time and the seasonal indicators. Okay. So we will use this TSLM function, right, to model both linear trend, the trend and the seasonal effect. Okay, so you indicate how many for example, the trend orders, t square, by t cubic, and whether you want to include the seasonal impact in your model. And this length of the season, right? And then whether it is a multiplicative model or additive model, okay? And then you look at the output, right? You look at the p-value of the result from your linear regression model, right? You look at the p-value. If the p-value is approaching 0, means the term in your linear regression model is significant, okay? And so we also we need to test whether the coefficient of the terms in your linear regression model is significant or not. So we can also consider whether your model can capture the trend and the seasonality impact of in your data. So you can use R square, right? R square or adjusted R square, right, to measure whether this model is significant or not. Okay. And yeah, this is the decomposition of the variance analysis of variance ANOVA table for time series. And so here you look at whether the trend impact is significant or not, the seasonality impact effect is significant or not. You look at the p-value, right? And all the joint impact of trend and seasonality, okay? And if they are not significant, you might consider, for example, in this case, only the trend is significant. So you may only fit a linear regression model in terms of trend. You don't need to consider the seasonal impact, the trend and the seasonal impact in your model. So you look at for example, whether the linear regression model is significant or not. You look at the p-value of this F statistics on the whole model, right? If this p-value is approaching 0, means your model is meaningful. Okay. We also learn some other, for example, this mean error or root mean square error, something. These indicators to measure whether the model, the fitting of model is good or not, right? The goodness of fit of your model. Okay, then we can use your model to do forecasting, right? To do forecasting. The critical part is you need to know whether if your model has seasonality terms, right? You need to clearly understand whether the future period is in certain seasons or not, right? If in a season, then this seasonal indicator will be 1, and all the other L-1 seasonal indicators will be 0, right? So you need to know whether the time is in that season or not, okay? And we can use TS forecast to do the forecasting in R, right? So your TS forecast and specify the model you fit it, and then how many period you want to do forecast. And when you plot the data, whether you just want to plot the forecast data or not. Okay, so this TS forecast function. Okay, so after you fit a linear model, maybe in terms of the trend, in terms of the seasonality, then you want to conduct the diagnosis of your linear model. Okay, so you will look at the residuals. Okay, in the residuals, it is the same as in linear regression models, right? And it is just an application of linear regression models in the time series with the time series data, right? So you need to check the residual, whether the residual follows a normal distribution, whether the residuals are have a normal distribution with mean 0 and constant variance, and basically whether the residuals are IID in normal distribution with mean zero, a constant variance, right? And then the independence test, right? So all these tests you need to look at. For example, you look at the normality test, you use a Shapiro and a Wilk test, right, to see whether the residuals are normally distributed, or you can plot the residual using QQ plot, right? If all the data, all the residuals are lies along a 45-degree line, that means it is approximate normally distributed, but the residuals. And of course, you look at the mean, whether it is zero, right? You can use the location test, right? And or you can just plot the residual according to the time. Okay, that should be, the residual should be distributed along on the time axis. Okay, and independent test, and you can use Elgin box test to see whether the residuals are independent, right? Of course, you can plot the autocorrelation function of the residuals, and if they are independent, means the autocorrelation should be approach zero, right? So you can use TS explore function in this TS forecast package, right, to see those tests and look at the p-value. Okay. And but in seminar 3, we did not cover the stationarity check of your residual. Basically, this is ADF, the unit root test, right? And if you didn't reject the null hypothesis, that means there is a unit root. That means it is stationary, right? And there is a unit root. Okay. So we will cover the ADF test in, I think, in seminar 5. Okay, you look at the distribution of the residuals, okay, and you can make a judgment. Here you can see here the variance becomes bigger, right? So the variance may not be constant, or the residual may not follow a constant normal distribution with mean and constant variance. So there may exist variance clustering, maybe heterogeneous variance or heteroscedasticity, right? So this will, you may consider in future, you might consider how to improve the forecasting by maybe fitting a gauge or arch or gauge model, right, in terms of the variance of the residuals. All right, so yeah. So then we discuss the simple or so-called moving average, right? Simple moving average, because now we want to deal with cycles of that. We want to smooth the data, right, in your time series. So we use simple moving average, right, to do this smoothing. And the simple moving average, we can use that to smooth the data. We can also use the method to do forecasting, right? So this is we have we can apply the simple moving average method to do forecasting. Okay, so we can use this TS move average function, right, to do the forecasting. And all the three means you use the recent 3-period data to do the forecasting, and this is a simple moving average. Okay, and we also discussed the simple exponential smoothing, right? Simple exponential smoothing, basically, it is also a method we can use to smooth the data. And this alpha is a smooth parameter. And yeah, this is simple. Usually, alpha is small. So between maybe 0.05 to 0.3. Okay. But in our package, if you did not specify alpha in your model, so the R package will do the best, estimate the best alpha for you, right? Based on the least square principles, right? To find a parameter which minimize the mean squared errors, total mean squared errors. So this is a simple moving average. We can also apply this method to do the forecasting, right? But remember, when you do the forecasting, you can only do maybe one step forecasting by using the simple exponential smoothing method, okay? And because of all the future values from t to t plus 1, right, you do not have the observation, so you will just you can see substitute your estimate of forecast, and then you can see all the future period from t plus 2, and then they are exactly, the forecasted value will be exactly the same as the forecasted value at period t plus 1, okay? This is a simple exponential smoothing, and you can use this TSESM exponential smoothing function, right? TS exponential smoothing, and you need to specify order equal to simple, okay? Because later we will have a double exponential smoothing. We have a hot winters method, okay? And of course, when you fit using a simple exponential smoothing to do to fit the data to do forecasting, right? You can also look at, for example, those indicators, for example, AIC, this conditional maybe for small sample data, and BIC criteria, right? All these information criteria to select which alpha is the best model, right? Alpha is the best parameter in your simple exponential smoothing model. If you did not specify alpha, so R will estimate the best fitting value for you, okay? Yeah, you can use TS forecast function to do the forecasting, okay? Plot the forecasted value or some use the plot function. Then we consider the, if your data have a trend, right? Now your data have, when you use a exponential smoothing, you want to smooth the data, and there are maybe cycles, fluctuations. Now if your data also have trend, right? So we can use this double exponential smoothing method, okay? So this method, you can see there is a two exponential smoothing function, the level and the trend, okay? And there are two parameters, alpha and beta, okay? And then when you do the forecasting, so in each step forecasting, right? Standing at time t, you do each step forecasting. So it will be the level at time t plus h times this trend bt, h time bt, okay? So this is the forecast value. Yeah, when you use TS ESM, TS exponential smoothing function to model the double or hot exponential smoothing model, right? You need to specify order equal to hot, okay? And you need to give the parameter values of alpha and beta. And if you didn't specify that, I will estimate the best value for you, okay? You can use the TS forecast function to do the forecasting. Now the hot winters. Now if your data has also clear seasonalities, right? So seasonality. Now you can use this hot winters method to smooth the data and do the forecasting, right? So there are three exponential smoothing function: LT, level, trend, and season. Okay, these are the three. So you have three parameters: alpha, beta, and gamma. Okay. And then when you do the forecasting, so this will be, for example, H step forecasting. So the level at time t plus the trend H time bt, and the seasons in your most recent seasonal cycles. Okay, the same season. Okay. So this is the hot winters method. Okay. And when you use the TS ESM function, you need to specify order equals to hot winters method. Okay, and then you give the parameter values for alpha, beta, and gamma. And if you didn't specify those values, I will estimate the best value for you. And you can look the AIC, BIC information criteria to compare which model best fits the data. Okay. Then you can use TS forecast function to do the forecasting. Okay. And now the last part we discussed model evaluation, right? Model evaluation. Basically, you may fit different models. For example, even if you use a simple exponential smoothing, you might use different alpha, right? Which model is best, right? Which model is better, right? So you can consider different criteria. So you can use different indicators to compare different models and select the best model. Okay, so usually we look at the AIC information, right? And we look at the BIC information, and the lowest the better, right? And you can use summary function to look at your fitted model, and then the model will display those indicators, right? The AIC, BIC, and also include many those error, for example, mean error, root mean square error, something. Okay. So you usually we look at this information criteria will be enough, right, to compare different models and select the model with the lowest, right, AIC or BIC values. Of course, you can use the TS model evaluated function to print those indicators. Okay. All right. So this is what we discussed in seminar 3. Okay. So now let's go to seminar 4. So in seminar 4, so now we are still dealing with in seminar 3, we are dealing with non-stationary data. So we want to look at the trend cycle seasonality, right? Now in seminar 4, we will discuss the stationary time series models. Okay, so first we need to understand what does stationary mean, right? Here actually in for time series, when we discuss stationarity, right, of a time series, we mean so the mean and the variance of the time series data were constant. So basically, it refers to the weak stationarity. So in time series, we also have a strong stationarity. So the strong or strict, the strict stationarity refers to the joint distributions of for example, this is x1, right? x2, for example, xn, xt. Okay. Suppose this time series have you can observe t data points. So actually, we mentioned in seminar 1, each actually refers to a random variable, but you just observe one data point, right? So each actually refers to a random variable, but only one data point realized, and you observe a sample. Okay, this sample is your time series. Okay, so when we discuss the stationarity of time series, the strict stationary requirement is that the joint distributions of a given length of those random variables is the same as if you switch this, for example, x1 to x5, is the same as the joint distribution of x2 to x6. So on and so forth. Okay, so this is a strict stationary requirement. So for the weak stationary requirement, we say as long as the mean and the variance were constant, okay, and for all observations, then we say this time series is stationary. Okay, so because each actually, is a random variable. Although you just observe one data point for this random variable, right? Okay, so the mean and variance are constant for all observations. Okay, so the mean of xt is the same, is a constant. The variance of xt is a constant. Okay, so look at it because they are random variables, right? So for this time series, so as long as you have a constant mean and variance, we say this time series will be a stationary time series. Okay, and because this stationarity requirement actually reduces the computational complexity, right? So if, for example, if the mean or variance of x1 is different from the mean or variance of x2, then you can say you have too many population parameters, right, to estimate. So that is sometimes cannot finish this job because you only have one data point from each random variable, right, in each period. Okay. So we say we require the mean and variance are constant, basically the second movement, right? Okay. And so with this stationary requirement, and we can ensure that the forecasting confidence and precisions will be within a so-called acceptable or maybe range. Okay. So if let's look at a simple example. So these two data time series actually are not stationary, right? Because you can see this is a clear trend, and the mean will be different, right? For example, in this time point, the mean is here, but come to this point, the mean becomes bigger, right? This is an increasing trend. And the second time series is also not stationary because you can see the variance becomes bigger, right? The variability becomes bigger. There are clear cycles, okay? So now, if suppose we don't have this stationarity requirement, so if you use, for example, half of the data points, right, to do the forecasting, so you are standing here, you use the previous this much data, right, to do the forecasting. Then you can see definitely your forecast will not be able to if you use the whole data set, right? If you look at the whole data set and your forecast will be standing this point, okay, so that there will be big errors, big gap. And this is similar. If you use, for example, the maybe the first portion of the data to do the forecasting, and their variability may be small. However, if you look at the whole data, and then your forecasting will be you standing here, this time point, right? And then you can see the variability must be bigger, right? So you may underestimate. In this case, you may underestimate the variability of the data because you use less data, and the data is not stationary. Nicholas, stationarity does not necessarily mean the data have a seasonality. Okay, so here just look at if your data have seasonality, your data is not stationary for sure, right? And but if your data have trend, your data is also not stationary. If your data have cycles, right, your data is not stationary. So your data have seasonality is just maybe one cause that the data is not stationary, the seasonality. Okay, the existence of seasonality is just one, could be just one of the reason that your data is not stationary. All right, yeah. Nicholas, are you okay? Okay, yeah. So your data have seasonality. Definitely, your data is not stationary, right? Because you have cycles. Okay, yeah. All right, so let's look at yeah. So this is why we need the data to be stationary, okay, and we need to ensure the constant mean and variance so that we can do make sure or ensure the forecasting error or margins are within the acceptable range. Otherwise, your forecasting may be the gap will be huge, depending will be affected by the data you are using, right? The different data you use, you will have a different forecasted results. Okay, so it's not what we want, right? So we want to ensure that we have a stationary data when we do the forecasting. Okay.
Sorry,
So for
Prof.
example, unstable forecast, if your data is your time series is non-stationary, right? And unstable forecast, and because the mean are different, right? And the variance are different, right? You may overestimate the autocorrelations. So especially if your data have trend, have seasonality, and the correlation will be bigger, right? The correlation will be significant from different from zero, okay? And yeah, this correlation may be overestimated, right, by the trend in the data, okay? No. What remember these are the random variable. We say the mean I think each we say the each remember, for example, you have a t period. So each period actually is a random variable. You observe one data point from this random variable. Okay, you observe one data point from this random variable in your time series. Okay, your time series actually is a sample. Okay, is a sample from a series of random variables. Okay, each time there is, so the your this measure is the random variable. Okay, but you only observe one data point. What we mean is this is the mean of this random variable, and the variance of a random variable is constant. It does not say that when you plot your time series, it is a horizontal thing, okay? And because this is just one observation of each random variable, and all these observations form your time series is a sample, okay? So this is what we mean the so-called the mean or variance refers to the random variable in time t, okay? So each time t, actually, it is a random variable, but you only observe one data point, small xt, okay? Small xt. So we require the mean and variance of this random variable is constant. So this so-called, if we have this assumption, we can guarantee this assumption, then we say your time series will be stationary. And because you only have one sample, which is a time series, so we look at you plot your data. If your data is something like this, so you can see the mean is quite stable, or the variability is quite similar. So we say we may look at the line plot of your time series. You can say it is stationary. However, we need to do we need to use other statistics, right, to test. For example, later we will use autocorrelation function, partial autocorrelation function, right, to test statistically check whether the time series is stationary or not. Okay. Yichen, are you okay? Are you clear? Okay, great. So if your data have trend, for example, if you plot your time series, your time series have this clear trend, then when you calculate this autocorrelation, and you will have autocorrelation will be significant from different from zero, and they have long period correlation, right? Okay, and you might also distort the seasonality in your time series. Okay, because if the trend dominates the composition of a time series, seasonality may be distorted and neglected in the forecasting process. Right here, you can see we may have a seasonality, but if you look at the trend, and this trend may dominate this time series, and the seasonality effect may not be captured. Okay? So this is why we need the time series to be stationary. Okay, and now we can use Corey logarithm, so different statistics, especially this autocorrelation function ACF and partial autocorrelation function PACF, right? To look at to test your data, whether your data can be considered as stationary or not. Okay. So we discussed how to calculate the autocorrelation, right? And also I think our course leader also prepare a few videos, right, to help you understand how to calculate the autocorrelation and partial autocorrelation. Okay, so the autocorrelation of a time series with trend, you can see this is a very important characteristics. Okay, so the time series with trend, the autocorrelation function will decay slowly with increasing lags. You look at this, the time series, you look at the autocorrelation function of a time series. You look at the ACF, right? With the lag increase from 1 to 12. Remember, if the lag is 0, means the autocorrelation function always equal to 1. Okay? And from 0 to 12, the autocorrelation function decreases slowly. You can see decreases slowly, but significantly different from 0, right? This blue area refers to the two standard deviation. Okay, if it is that actually there is a theorem behind the autocorrelation function. If they have no correlation, they follow a normal distribution, something like that. And you can see if the time series have trend, the autocorrelation function decreases slowly with increasing lags. Okay, because when a time series exhibits a trend, autocorrelation mistakes this trend pattern across time as the percent correlation across lags. So remember these characteristics. Okay, so for a time series with clear trend, the autocorrelation function will decrease slowly with the lag increases. Okay. This we will say decrease exponentially. Okay, decrease exponentially. And this means decrease slowly. Okay, so decrease exponentially means after certain lags, for example, after lag 5, and then all the autocorrelation will be within 2 standard deviation. Okay. Nicholas, so this is, yes, you can see the autocorrelation for the first graph. So it's a stationary time series, the autocorrelation function. We say it decreases exponentially, and after certain period, all the autocorrelation will be within 2 standard deviation. That means we can treat them as almost 0. But for this time series with trend, the autocorrelation function, you can see decrease slowly, and they are not within two standard deviation of this graph, right? So this is we say sometimes you can say if, for example, you have many autocorrelation function, for example, from period 0 to up to period 20, 30, depending on the size of the data in your time series, right? And later, actually, we will show, for example, some of data, for example, activity 4.1. We can plot the first 60 legs, right? The autocorrelation function, partial autocorrelation function for the first 60 legs, right? You will look at if 5%, okay, more than 5% of the autocorrelation function is beyond, okay, is beyond the 2 standard deviation, we will say they may not have, actually we say they do not have a cutoff, and they decay slowly or exponential something, right? Here, remember, for the time series with trend, the autocorrelation, even if, for example, you trend up to even 24, even 36, and then the autocorrelation will still beyond the 2 standard deviation range. Okay, so we say they decrease slowly or decay slowly. While for the stationary time series, and after a few period, okay, after a few legs, the autocorrelation or PACF, ACF or PACF will be within 2 standard deviation. So we can say they decays exponentially. Okay. Nicholas, are you okay? Okay, great. Yeah. So this is a partial ACF, right? Partial autocorrelation function with lag K. And this partial autocorrelation means you want to remove the impact of, because when you calculate the relationship between, for example, YT and YT minus K, but in between you have y t minus k plus 1 yt minus k plus 2 up to yt minus 1. So this impact on yt, right? Okay, so when you calculate the partial autocorrelation function, means you want to remove the impact of this the values in between. So basically, this partial autocorrelation function, if you fit a linear regression model between yt and yt minus 1, yt minus 2, up to yt minus k, so this partial autocorrelation function actually refers to the coefficient of this guy in that regression. Okay, means you control the impact of the other lagged values on YT. Okay, yeah. So if you are interested, you can refer to a textbook to understand what is a partial autocorrelation. Okay. Here again, for the you can see if we look at this, this is autocorrelation, right? And if you look at the lag, this one, right? The partial autocorrelation and the lag. With the lag increase, you can see actually still many, right? Many partial autocorrelation is beyond the 2 standard deviation. Okay, and this may also show there could be maybe seasonality in your time series. Okay, in your seasonality, if your time series have seasonality, that means your time series is non-stationary. Okay, so and of course this partial autocorrelation. For later we will discuss the autoregressive function AR model, right? Autoregressive model, and the autoregressive model with order P, so the partial autocorrelation will have cut off after leg P. Okay, so this ACF and PACF will help us to determine whether you can use MA model or AR model or AMA model, right, to model your stationary time series. Okay. And for partial autocorrelation, of course, lag zero does not exist because you cannot see the impact of yourself, right? And so does not exist. Okay. All right. So you can use the TX explore function to look at to get the ACF and the PACF from your time series data. Okay, so here we can, for example, for SP500 data, close that column, right? That theory, and you use TS-SEF and TS-PACF, and you can get the ACF function, the plot, and the PACF function and the plot. Okay, and if you look at the SAF and PSAF, you will see that the ACF, you can see, decreases slowly, right? In terms of the lag. While the PSAF, you can see this is period one, right? The lag one. After lag one, all the other PSAF is within 2 standard deviation, which means almost zero, right? So here for this SP500 data, and you may consider later, you will see, you may consider AR, you use AR model, right, to model this, maybe this AR1 model, because after the lag, with a 1 period lag, all the PSFs are almost zero, right? You can use AR1 model to model this SP500 closed data. Okay. All right, so let's demonstrate this example. Okay, so I guess we actually look at it, right? The TS-ICF or TS-PSF, right? We actually use TX Explore, right? TX Explore to understand our data, right? Okay, so let me go to the, okay, where is my, oh, here. Okay, so let me demonstrate what we can show in the slides. It's here. Okay. So we import the data. So first, we need to use the TS forecast library, the package. Okay. And then we import SP500 data. Weekly, okay, weekly CSV. Let's look at this data. All right, so this is data SP500. So the first column, date, name is date, and then close. But date, it is a character, so we need to change it to the date format. Okay. So it is day, month, and year, right? Okay, day, month, and year. Check. Okay. So we change the date into date format, and then we will remember when you look at the data, right? You want to see whether there are maybe empty data in the time series. Okay, so we will let's just do it. Okay, just use the approximate function to um, fill the missing values. Okay, proxy. Okay, so we fill the missing value using the interpolation method. Okay, interpolation method to fill up the missing values in closed column. Okay, and then we convert the closed column into a time series object in R. We use TS convert function. Okay. And we name it this column as P500. Okay, yeah. So this is what we did in previous three seminars. Okay, so let's look at this data, or you can print something. Oh, TS convert cannot find the function. Okay, maybe because we didn't use the TS forecast package. Okay, all right. Okay, great. So we convert the SP500 closed column into a time series object in R. So let's look at the ACF and the PACF of this time series. Okay, you can just use TS ACF and SP500 close, and you want to see maybe lag equals to maybe 20. Okay. Okay. So this is ACF for this SP500 uh, close data. You can see if you look at it, the ACF function, and we say the ACF decrease slowly, right? Because even if you have lag 20 up to 20 lags, and it is still different from zero, right? Significant different from zero. Okay. Okay. If you want to look at uh, the PSF, okay, SP500, maybe 20 lakhs. Okay. And you can see after leg one and almost all the other, okay, all the other PSFs are within 2 standard deviation, so they can be treated as zero, right? And so for this time series, you can consider using AR1 model, because for AR model, ARP model, so the PSF will have a cutoff uh, after leg P, okay, while the ACF will decrease maybe uh, decrease. Here, actually, if you look at this ACF, so still it's not a decrease so-called exponentially. So you may consider maybe extract some of the trend from your original time series, and then you redo relook at the ACF and PSF. Okay. All right, so this is ACF, PSF for SP500 time series. Let me go back. Okay, so yeah, so let's do a simple activity. Okay, simple activity. Now we compute and plot the first 60 legs of ACF, PSF of the arrival series. Okay, and then we look at those ACF and PSF, and we maybe have some observation. Okay, and maybe you can try with, I give you 2 minutes. Right, load the data, the arrivals. Remember to change the column name. Okay, change the column name from total arrivals to arrivals, and also fill up the missing value, and also convert it into a time series object, and plot the ACF and PACF. So have a try, okay? Everyone have a try, right? Try using R to import the data and just refresh your memory, right? You have done this in seminar 1 and seminar 2, seminar 3, and import the data into R and clean the data and do proper data preparation and convert data into time series, and yeah, you can yeah, look at the data, okay? Of course, you can also use a TS explore function. Right? You can use TS explore function to see the line train, line plot of your data, original data, and the ACF and PSF. Okay, so I believe everyone should be able to import data. So let me do a quick demonstration. Okay, let me do a quick demonstration. So we need to read the data, arrivals CSV data. And let's look at the column. I guess we need to change, okay? Yeah, we need to change the name of the second column because currently it is total arrivals. So we want to change it to arrivals and also change the date yeah, into the date format in R. Okay. The second equals total, right? Or arrival. Hmm? We change it to total, right? I remember we maybe total is easier to use, okay? And then we change the date into the date format. Is similar day, months, and a year. Okay. Okay, one enough. Okay. So now let's convert the total column into time series. Total and T equal and date. Okay, you can give a name. So maybe we don't need to give a name here. Total is simple enough. All right, so let's look at the ACF. This is by default. If you didn't specify the number of legs, so the number of legs will be 8, okay, by default. And if we want to maybe we want to see how many 60 legs. Okay, so these are the 60 PACF. If you look at this up to leg 60, so the ACF is still not significant different from zero or not within two standard deviation, right? So not within this blue area. So means we can say it decreases slowly, right? It decreases or decays slowly, right? So clearly there are trend in this data in this time series. Okay, and now if you want to look at the PSAF, okay, 60. Okay, so let's look at the 60 PSAF. So if you look at the 60 PSAF, and if you look at this PSAF, you can see in certain period, for example, with leg 2, 3, leg this maybe 7 something or this, or if you look at this leg 12, this should be 12, and the PSF is beyond the beside the two this blue area or the two standard deviation curve, right? And it's again in other maybe leg 24 and maybe this leg 36, right? So it is significantly different from zero. That means there could be clearly seasonality in this data. So we know from the ACF decays slowly. So it indicates there are clear trend in this data, in this time series. And if you look at the PSF, also there are in certain legs, right? Leg 12, leg 24, leg 36, and the PSF is significantly different from zero. That means that your data have seasonality. So the data have both trend and seasonality, the original data. Okay. So you can try to see, you can use TS Explore. Okay, let's see. We don't specify any parameters. Let's choose the default setting. So you can see you have clear trend, right? Clear trend of this time series, and there are also seasonality. Okay, seasonality, because it is a monthly data, right? Monthly data. So seasonality. Okay, the seasonal length is 12. Okay. So this also shows the SEF and shows the PSEF. All right. Okay. Let me go back. Yeah, so from the ACF and the PSF plot, we can clearly maybe see the trend of see the patterns or characteristics of this original time series. So it has a clear trend based on the ACF. It has seasonality or cycles, right, based on the PSF. Okay, so now your data is not stationary, right? Your data is not stationary. So in seminar 3, treating non-stationary data, if we want to focus on the certain part, for example, the trend, the cycles, the seasonality, we can use simple moving average. We can use exponential smoothing. right? We can use Hortus method, hot windows method, right, to extract the certain part of the the characteristics of the time series, right? Okay, Nicholas, you mentioned the stationary test is significant. Stationary test, you mean uh, the uh, the ADF, right? Okay, let me go back. Let me go back to see the arrivals. Okay, let's look at stationary. Okay, here remember this ADF test. The null hypothesis is there exists a unit root. If a time series has a unit root, that means your time series is not stationary. Okay, this you reject. Okay, this arrival, this is referred to the ADF, the unit root test. Unit root, yeah. And so that so later we will discuss the unit root test. Use ADF, the ADF test. Okay. And here we focus on this ACF and PSAF. You look at these two plots, you see, wow, the data definitely not stationary, because for stationary time series, the ACF should decay exponentially, and the PSAF will also, you can say, decays exponentially. Okay, and so here we will let's go to the yeah. Okay, so now we are dealing with so with a certain trend or certain part of you want to extract a certain information from your time series. You can use simple moving average, you can use exponential smoothing, those kind of method, right? Now we are using another way to treat, because the time series is not stationary. So what we are doing is we use differencing. Okay, we use differencing to remove the trend, to remove the seasonality. Okay, so there now we use, you can say this is a stochastic method. In the previous we use those linear regression to get the trend. We use moving average. We use exponential smoothing, right? Those are we get the so-called those trend and seasonality. Now we use the differencing to remove the trend, to remove the so-called the seasonality. Okay, so to make the time series to be a stationary time series. Okay, so this is what we are going to do. So let's look, Nicholas. So what happened? So opposite. Okay, Nicholas, maybe if you have questions, we can discuss. Okay, previous means the ADF test. Okay, ADF test. Your null hypothesis is there exists a unit root. Yeah. No. I need to be clear. So the ADF test means the null hypothesis there is a unit root. The unit root means you need to do, so the unit root test means you can see YT. Okay, maybe I write here. Okay, YT. Okay, when you fit a AR1 model, okay, equals maybe this constant plus we use AR1 model. Okay, phi 1 YT minus 1. Okay, this is just an illustration. Okay, and plus epsilon t. Okay, So here ADF test means we want to see whether if this phi 1 is equal to 1, means this AI1 model is not the stationary. Means we want, later we will discuss, if we need the coefficient in the AR model, those phi 1, phi 2, and they must meet the stationary requirement. So here the ADF test means roughly we say whether the null hypothesis whether phi 1 equals to 1. Okay, this is your null hypothesis. And this ADF test means if it is, remember this ADF test, we have different forms. Maybe there is a trend, maybe there is no trend, right? This kind of different forms when you consider the test. And so this uh, uh, so we can also, if you do a difference, means for example you take a difference nebula t maybe yt. Okay, this will be suppose, okay, suppose there is a unit root. So we use maybe, for example, rho nebula y t minus 1. So this is another form. So we will do the IDF test. So this says rho equals to rho equals to 1. This is another form. So we focus on maybe the difference theories. Okay. So if the significance p-value of this ADF test is different from, for example, less than 0.05, so we will reject, for example, in this form, reject the null hypothesis. Means there is a unit root. A unit root means the data the time series is not stationary, right? Because you need to do a difference, maybe first order difference, and then you can make the time series stationary. Okay, so now let's look at this stationary seems we reject, right? Well, I think you say we reject this ADF test because ADF means the p-value is less than 0.05. So means it is seems stationary, right? Maybe later we can discuss. We can discuss what happened with this. Okay. So here you look at the location. Location you reject. Mu is not 0, right? Clearly, right? Normality is not. You reject the normal assumption of your. This test should perform. This should perform on the residuals. Residuals. Okay. The L box test independence, you also reject. They are not independent, right? Okay, but for stationary means these residuals, I believe this focus on the test focus on the residuals. For example, you fit a simple linear regression after this AR1 model, and then you fit this model, and you focus on the residuals, and then this stationary means the residuals are stationary. The residual are stationary, then you can focus on, for example, AR model, ML model, and even ARMA model to work on the residuals because there are still information from your residuals, right? All right, so Nicholas, we can discuss later, all right? Okay, so let me go back. Yeah, so now you can see if your data is not stationary, means if you use, for example, fit AR model or ML model or ARMA model, so your model will be in trouble because you cannot use, for example, linear least square method to estimate those parameters with, for example, we say efficient. We say if your residual meet those criteria. For example, IID normal distribution, right? IID normal distribution, then your estimate of your parameters, model parameters will be blue, so-called best linear unbiased estimator. But if uh, your data, right, is not stationary, and so your estimate or your forecast will be in trouble. So we need to ensure the data is stationary, right? Is stationary. So what we can do is, besides those methods in seminar 3, so in this we will use the difference method, right? The difference method is quite straightforward, right? Here, for example, we use yt minus 1. So this is a difference between the adjacent period, right? This nebula yt, okay? And if you look at this illustration, here we have a trend, right? Y1, Y2, and Y3, it is a trend. But you do a first order difference, then actually this refers to this trend. The trend could be a constant or stable or stationary. The trend, this is refers to this first order difference, could be a stationary time series. Yeah. Uh, when you this is actually the steps when you when you have a data, right? When you have a time series, uh, when you have a time series, you first need to check whether the time series, of course, whether you have missing data, whether you have maybe for example outliers, even significant outliers you want to remove, or you want to maybe do something on the outlier, something, okay, to do data preparation. So then you plot the data to see the trend, right? Whether the data has clear trend, cycles, or seasonality, right? If then you do a stationarity check using, for example, ACF, PSF, to see whether the data is stationary, the time series is stationary or not. If the data is not stationary, whether you want to remove the certain so-called components, those trend, seasonality, cycles, right? And then you will convert the data into a stationary time series. With the stationary time series, then you will use the method we are looking today: AR method, AR model, MM model, AMA model. Okay, so basically you will look at the data. Uh, uh, do we need to read these tests of residuals? The residuals usually, so once you fit a model and then you have a residuals, right? And then you will use the residual to check whether your model is, extract the necessary information or not, right? For example, if your residuals, we discussed in previous semesters, if the residuals is uh, so-called white noise, means you extract all the information from your time series, so your analysis work is done. You don't need to perform further analysis. But if you look at the residual, if the residual is stationary, it's not white noise, then you still need to continue with this AR model, MM model, AMA model, right? And also, if you are dealing with, for example, the variance, you look at the variance of your residual. If the residuals have maybe a not homogeneous variance, you need to consider those arch model or gauge model. So this is actually the procedure of the modeling part in terms of time series. Yes, once you have the model, right? Yeah, you need to look at the residual to test, to check, to evaluate your model. Yeah, you need to read the residuals, right? You need to look at, perform the residual analysis. Okay, difference I think is quite straightforward, right? So you just use, for example, yt minus 1, and you will get the first order difference. And then and then you want to continue with maybe the second order difference, right? So you on this time series, you do one further step difference, and then you can see previously it is a quadratic shape. So because you can see this is 5 square, 6 square, 9 square, right? 8 square, 7 square, 8 square, 9 square. And then you do the first order difference, you get a time series, this nebula YT, and you can see the time series becomes a linear trend, right? From 11, 13, 15, 17. And then you do a second order difference, you will have a constant time series. So this is actually the rationale behind. So for the time series with a trend, right? You can, if it is a linear trend, the first order difference will enable you have a stationary time series, right? If the original time series is quadratic or even cubic trend, then you do a second order difference or even third order difference to make a stationary time series. So this is the idea. Difference can extract the trend information, right? The trend in your time series. So YT has a clear trend, right? And but you do a first order difference, you can see it becomes a linear. And then if you do a second order difference, right, it becomes a constant, right? So this is the idea behind. We use the difference to extract the trend information or remove the trend in your original time series, and to make your time series a stationary time series. Okay, so the difference actually you can see if you look at this, if you look at this, yeah, this is nebula YT. This is nebula YT minus 1, and the difference between the two will be nebula to the power of YT, right? Okay, so the second order difference, okay, and then so on and so forth. So this is nebula K. So this, if you look at this, actually, this is like an auto-regressive function of YT, right? If you put YT in one hand side and all the other in the other hand side, for example, YT in the left hand side and YT minus 1, you can see YT minus 1, YT minus 2, something in the other hand side, and plus this nebula K YT. So it's like an auto-regressive of YT with its past values, right? And plus this so-called the random term. Okay, because right, this is like this auto-regressive of its own past values. But yes, use difference can detrain the original time series. But if you use most order difference, you may have this so-called over difference issue. You may actually increase more variability to the time series, right? For example, here, so this is the original time series. So it is a clear linear trend, right? Linear trend. And for this time series with linear trend, the first order differences will be sufficient, right? If the first order difference will be this this line, right? This orange line, and you can see it makes the first order difference in series quite stable, right? The mean is like a constant, and the variability is not small. Of course, you can do the second difference. Okay, second difference. You look at this blue, right? This no green, this green curve, and you can see yes, still the mean is zero, mean is constant, but the variability becomes bigger, right? And if you do third order difference, and this is this red curve, so you can see variability becomes bigger. So actually, this the variance of your difference in time series becomes bigger. So this is the over difference issue. So this is why you can first plot your time series. Look at the trend, whether it is a linear trend or quadratic trend. If it is a linear trend, the first order difference will be sufficient to make a stationary time series. And then if it is a quadratic trend, so you use second order difference so to get the stationary time series. Okay. Okay, so this is the differences. Yeah, differences can help us to remove the trend, right? And remember in seminar 3, in terms of this trend, we can use, for example, fit linear regression with either t as the independent variable, maybe a t square, right? If it is quadratic trend, right? So now we are using difference, right, to get the trend, to remove the trend from your original time series so that your time series can be a stationary time series. Okay, so seasonal difference. Seasonal difference. So here you can see we use yt minus yt minus L. So if the seasonal length is L, right? So this nebula L yt. So this is a seasonal difference. Okay, and of course we can first do the first order difference. We get the nebula yt series, and then we do if you look at your first difference in series, and there's still maybe cycles or seasonality with length L, so you can further do this seasonal difference. Okay, so this is what we mean here. Okay. Of course, you can do so-called high order, right? High order for both simple and seasonal difference. For example, here you use k order difference, and then you do a seasonal difference with length. The seasonal length is L, right? And maybe there are S seasons, right? S cycles in your data. Okay. So this is so sometimes the notation could be very complex, right? So this nebula L refers to the L step difference. Usually it is a seasonal difference. This S refers to the seasonal. There are S cycles in your time series, and this nebula, for example, K refers to the K order. Okay, K order difference. Okay, so well, this the original time series is yt. So nebula K yt refers to you do K step difference. First nebula yt, and then nebula square yt, and then nebula the to the power 3 yt something. Okay. So in some textbooks, we use some maybe operators. Use some operators to indicate this. For example, you use B indicator. This refers to the one step backward. So this we mentioned in seminar 2. This is the backshifting, right? Backshifting by one period, right? So some of the textbooks they use some operators to make it simple. Okay. Okay, so let's look at the seasonal difference example. So here this is a time series, and there are 4 seasons in a cycle. Right, the cycle length is 4, and for example, quarter, right? 1 quarter, 2nd quarter, 3rd quarter, 4th quarter, right? And then you can see this is nebula. If the subscript is 4, refer to yt minus yt minus 4. Okay, so means here you will lose 4 data points, right? Because you will have y5 minus y1, y6 minus y2, right? So y6 minus y2, y7 minus y3, right? So on and so forth, right? So this is your seasonal difference series. Okay, so we use this nebula 4 YT to indicate this difference, seasonal difference series. And if you plot the data, for example, the original data is blue, right, YT, and then you do the seasonal difference, you have nebula 4 YT, and you can see you will lose the first 4 observation, and then you can see it becomes the variability becomes smaller, and of course there are still exists so-called maybe these cycles. Okay. Yeah, so this is yeah, so although the signal effect still remains but becomes stable, right? And the difference becomes I mean the variability becomes almost a constant or smaller. Okay, so this is a seasonal difference. The thing is, for the seasonal difference, you need to ensure that there are clear seasonal cycles in your data, and you know the length of your seasons, right? The length of your seasonal cycles. Okay, you can do this seasonal difference to remove maybe the variability of the season effect. And another thing you can consider use a log transformation to stabilize your time series. This is especially a useful method in terms of financial time series. Okay, in financial time series, for example, you are dealing with maybe the returns, and you take a log transformation, and the returns actually uh, is use log transformation. You can easily interpret the difference of the data points. Okay, and here, so you take a log transformation of your original time series, but ensure all your time series should be positive, right? Your original time series, the data should be positive. Otherwise, you cannot take a log transformation, right? So this you take log transformation to remove the non-stationarity in terms the variance, right? If you look at this, you can see the variability of the variance may become bigger and bigger, and you take a log transformation, and then it becomes a stable, a stationary time series in terms of variance of your original time series. But the trend still keeps, right? And because YT becomes bigger, and the log YT still becomes bigger, so the trend can keep. So you might consider this YT star series after tag log transformation. That could be still trend. You need to detrend, right? Remove the trend and make this stationary time series. Okay, because you take a log transformation, if you do forecasting, right? So you need to put it back, right? The e exponential back, right? When you do the forecasting, okay? So basically, the idea is for difference, we can use the difference to remove the trend, right? Remove the seasonality, right? And reduce the variability, right? Remove the maybe the heterogeneous variance in your time series, and you use log transformation, right? So this different method, and so we want to have a stationary time series so that we can fit with AR model, MA model, or ARMA model. Okay. So we can use this TSD function, right, to do the difference. Right, so this is quite straightforward, and you will have a new time series and with first order difference. And you can use the log function to transform your original time series and remove the maybe the heterogeneous variance issues. Okay. All right, so I think it's quite straightforward, right? For this uh transformation, right? Use the difference. We use uh this TSDiff function. Remember in seminar 2, we also use the TS lag function, right? So we use the TS lag function to get the back shifting or forward shifting series. Okay, that different here. This TS diff is where you get the difference in series of your original time series. Okay, so we create a new column in SP500 time series. Right, close. First or difference, so TS diff and SP500 close. Yeah. So this will give you a new time series. You want to see uh is a new time series D1, right? Okay. So it's a new time series, and uh here the first observation will disappear because you use y2 minus y1. So this you don't have a observation in this time series. And we also can create a log transformation. Okay, SP500 log close. Just use log SP500 close. Okay, ensure because SP500 all data are positive, so you can take a log of all the data points. Oh, okay. So this is you take a log. Okay. Yeah. So this is let's go back to the slide. So let's look at the stationary property of the arrivals series and perform differencing and log transformation to the series in R, okay? And explore the different and logged series and discuss whether the transform series is stationary or not. So basically you can see you need to perform difference and you need to uh, perform log transformation, and then you check the stationary of the new series. Okay, I give you 2 minutes to have a try. Okay, it's quite straightforward, right? Okay, so let's do it together. Okay, so we focus on the arrivals, right? Arrivals time series, and then we take a first order difference. Okay, let's generate this. Okay, generate this arrival total difference order one equals TS diff. Okay, arrivals total. Okay, and you want to print arrival total. Okay, so it is a monthly data, right? Monthly data from 1961 to 2025 for December, right? Okay, so now we want to see whether this first difference is stationary or not. First difference series is stationary or not, right? So you can get the SEF or PSF of this time series, or you use TS Explore to see maybe let's say lag maximum lag equals, let's see 6t. Let's see whether we have for we can generate. Okay, so this is a series plot of your first order difference in time series. If you look at the line plot, you will see that the variance actually is not constant, right? The variance becomes bigger and bigger. And if you look at the trend actually, or the mean, uh, red line refers to this linear trend. So there is clearly a linear trend, right, from zero, and this not a constant. And if you look at the distribution of the data points, and if you look at the QQ plot, clearly it's not normally distributed. It's not normally distributed, right? If you look at the ACF plot, you can see the ACF plot, and they have for certain period, the lags, the ACF is beyond the blue area or the two standard deviation, right? So clearly the ACF is not uh, does not decay exponentially, right? Or and it decays slowly, right? Up to like 60. Okay, and these are the autocorrelation in certain lags, so it's very big value, right? And if you look at the PACF, again, you can see the PACF is, you can see it is definitely not zero, right? Almost very big beyond this two standard deviation area, or you can see maybe a 95% confidence interval. And then the ACF actually for many legs, it is still significant from zero, different from zero. Okay, so if you look at the line plot, of course, this first order difference in time series is not stationary, right? It's not stationary. If you look at the plot, if you look at the ACF, PACF, okay. Okay, if you look at the test, okay, statistics with autocorrelation test, okay, here this location is not zero, right? Because uh, yeah, you can see maybe similar. P is bigger than 0.05, and so we cannot reject the null hypothesis. Okay, location maybe can approach zero. Okay, and normality. This should refer to, yeah, I think this should refer to the residual after you remove the trend. So this is why you reject the normal. It's not normal. If you look at the residuals are not normal, right? And ADF, okay, ADF you reject. So reject means it is stationary, right? Residual are stationary, right? So you need to do further, right? L, L box, you reject the null hypothesis. So they are not independent. So the residuals are not independent means you need to, you can consider they have correlation. So you will perform AR, MA, or even ARMA model, right, on the residuals. Okay. All right. So this is the first order difference. So let's look at the log, because if you look at the first order difference, the variance becomes the variance is not a constant. So we take a log transformation to see whether we can stabilize or make the time series, the log transformed time series, be a stationary time series. Okay, so let's create a log. Okay, arrival total log. Okay. So we look at the log transformed time series. Let's look at the line plot. If you look at the log transform time series, the line plot, okay, and the variability becomes, yeah, you can remove the maybe different so-called a heterogeneous variance issue, okay. And but if you look at there is still a clear trend, right? We mentioned the log transformation can remove the heterogeneous variance, right? Because it makes the scale become smaller, but the trend still exists. So you have this clear trend. While the first order difference remove the linear trend, right? So here you still have this trend, and this trend seems you can see maybe linear, right? So you can perform the first order difference on this logged time series, right? For on this new time series, and then you can get maybe remove the linear trend. Okay. And if you look at the QQ plot, clearly the residuals, or not residual, this refers to this log time series. So they are not normally distributed. Definitely it's not normally distributed, right? And if you look at the ACF decay slowly. Okay, maybe we can explore maybe with lag equals to 60. Okay. If you look at the ACF, right, decay slowly but not exponentially. So means not stationary for sure, right? So there is clear trend in your this log time series. Okay. If you look at the PACF, right, still there are in certain legs, there are spikes. That means there are seasonality, right? Seasonality in this logged transform series. Okay, yeah. So this is we can perform the test, right? Explore the difference and log the series, and so clearly the two methods, the first order difference and the log transformation, cannot ensure the transformed series are stationary, right? They are non-stationary for sure, right? This is non-stationary, so you need to do further. Maybe for this log, the transformed series, you need to do a further difference. Maybe we can try. Okay, let's try with the second or the difference on the log series. Okay, maybe we can choose let max to 60. Here you can see this is a diff series, the first order difference of the log series. And look at the QQ plot. Still, there are if you look at the beginning and the end period, a few many data points, they are not lies along this 45-degree line, but seems better, right? Seems better. And still here you can see the ACF. There are spikes. So clearly there are seasonalities, okay, seasonalities in this time series. And if you look at the PSF still, right, okay, so even if you do the first order difference on the log series, it seems if you look at the original this line plot, right, line plot, and there are still some patterns. For example, maybe this variance seems okay, but the trend, right, trend become decreasing trend, right, and there's still some trend, so means this is due to seasonalities, okay, actually due to seasonalities. And if you look at the ACF and the PSF, and they have spikes at certain legs, okay. Okay, so this is activity 4.2. So let me go back. Okay, are you all okay with this activity? Do you have any questions? All right, yeah. So basically, you look at the data, right, and then look at the ACF, PSF. You plot the data, and then you do difference. You do log transformation, and sometimes this method can still not be able to make the stationary time series. So you need to do further. Okay. So here we do a quick summary. Stationarity refers to the stability of time series. Basically, we say we have a constant mean, constant variance, right? And so it is very important for accurate and reliable forecast. And the trend, if a series with trend, clearly it's not a stationary, okay? It's non-stationary. And we can use ACF, PSF to detect the stationarity. And difference in the effective method to detrend a time series, right? And for linear trend, first order difference is sufficient. For quadratic trend, maybe second order difference will be sufficient. So this is the later we will discuss ARIMA model. This D will refer to the order of your difference, right? D equal to 1, the first order difference. D equal to 2, you need to do second order difference, and then you fit with an ARMA model, okay? So, but you need to avoid over difference because you will make the variance become bigger, right? Of your difference time series become bigger. So you can consider log transformation, especially for financial time series, and you have all the time series data are positive. Okay, you can remove the variance, heterogeneous variance issues. Okay. Okay, so now let's look at now suppose we have a stationary time series. Okay, we have a stationary time series, and the time series are not white noise. Means the time series data have correlation, right? And but they have a constant mean and variance. Okay, they have correlation, so we want to extract the information from this time series, so we can use this moving average model. Okay, this is not the same as the simple moving average we discussed in seminar 3, right? That simple moving average, we say we can smooth a time series. We can use that to make a forecast, right? We use simple moving average. but there are different things. Okay, here this moving average will depend on your so-called forecast error or observed disturbance, random noise. Okay. So this is just an example. You can see in the first day, your sales is 104. Your forecast is 100. Okay, how did it first come from? I don't know, but it's just an example. Okay, and then your error will be 4. So this error, this term will be used in your forecasting, in your model fitting. Okay, and maybe the second day, your sales is 96, but your forecast is 106. It's quite straightforward because you can see your sales is bigger than your forecast, then definitely you will increase your forecast in the next period. Okay, suppose it is 106. Okay, but your actual sales is only 96. The error is -10. Now because the error is -10 in previous period, so intuitively you will reduce your forecast in third period. For example, 95. Right? And however, maybe the actual sales is 109, so you have 14 positive. The error is positive 14. So naturally, you will increase your forecast in the first period, which is 1. Suppose it is 110. Okay, and then you realize the actual sale is 113, and then you have 3. You can see positive error, and still, and maybe due to the mechanism of the moving average model, and your forecast is 107 in period 5, and your actual sale is 108, and your error is 1. So you can see we have the forecasted column, we have the actual column, right? Actual sales column. And then these two columns will give you the error, the observed random or this noise. Okay. And then in the MM model, moving average model, we need to leverage on or utilize these errors in your model, in your forecasting. Okay. So this is a moving average. Okay, it's not the simple moving average we used in seminar 3. Okay. Okay, so we have this two data set, MS series 1, MS series 2. Now these two time series can be fitted by MM models, moving average models. Okay, so we will import the data and create the line plot and ACF, PSF, and let's look at what we can get. Okay, now try to import the data. Okay, try to import data in your R, and then we will see what we can observe. Okay, from the plot. Okay, to save the time, so I need to be faster. Okay, so let me import the data. Okay, let me import data. So MA1. So these are the MA series, right? Series 1. Okay, so this is a series. So I will change the column name. And for this series, we don't have a missing value. Okay, so I just need to change the first column into date format. Okay. Okay. Yeah. It will be a year, month, day. Okay. Yeah. Year, month. Oh, it's in this format. Okay. Okay. And we convert this to time series. Okay. Let's check. Okay. All right, so this is the time series MA1 series, okay, MA1 series. And similarly, let's also import MA2. So I just copy, okay. MA2 series is to data into this into R. Okay, it should be the same. All right, so MI2, let's look at MI2. Okay, so these are two data sets. Okay, two data sets. So let's look at the line plot, right? Or we look at you can use a TS Explore, okay? TS Explore, let's look at the TS Explore. Maybe I with lag, maybe 30. Okay. So if you look at the line plot of MA1 series, uh, you can see this is the variability seems not an issue, right? And the data distributed around the mean, and but there are seems the trend line is decreasing, right? And if you look at the QQ plot, and some data points is not distributed along the 45-degree line, so they are not normally distributed. And if you look at the ACF, okay, looks okay, because the leg 0 is always 1, leg 1 is among 0.5, and all the other ACF with legs bigger than 2, bigger than 1, from 2 I mean to up to 30, you can see the ACF is between the blue line, blue area, between the this 95% confidence interval. Okay, you can say they are almost zero. So we can say this ACF decays exponentially, right? Because up to leg 30, the ACF almost zero, right? And then you look at the PACF. Let's look at the PACF. PACF, after maybe leg 1, 2, 3, 4, 5, 6, after leg 6, right? The PACF seems are also almost zero, you can say, right? Between this blue area, and we said within 2 standard deviation, I mean the mean 0. Okay, so we said they are almost 0. So here, if you look at the SCF and the PSCF, yes, right, this is the typical characteristics of stationary time series. They have correlation, right, in short term, right? They don't have a trend, right? Because if the time series have a trend, means the SCF will decay slowly. But here you can see decays exponentially, right? Only after period 1, and then it becomes you can say 0. Okay. And remember, this ACF we have a cutoff after leg 1, right? So this is a typical characteristics of MA model, right? MAQ model. And after leg Q, so there is a cutoff. Okay, here you can see after leg 1, the ACF you can see the ACFs are 0. So we can use MA1 model to model this time series. And for MA model, the PACF actually is you can say decay exponentially, and they don't have a cutoff. Okay, this is a characteristic of MA model. So this is MA1 series. Okay, so let's look at the MA2 series. Okay, TX explore MA2 series. Okay, lag max equal to 30. Okay. And if you look at the variance of this series may have some problem, right? Some of the maybe small and then the other become bigger. And especially beginning and end, right? The variability is bigger, you can say that. And the QQ plot, yeah, they are not normally distributed, right? And not normally distributed. And if you look at the ACF, okay, ACF, so you can see after leg 2, the ACFs are within this blue area means 0. Okay, so there is a cutoff after leg 2. Okay, for ACF. While for PACF, and it also decreases, right? And also after leg 1, 2, 3, 4, 5, 6, after leg 6, and you may say they also become 0. Okay, so but if we look at the ACF, so clearly it is the pattern is very clear. So we can use a MA2 model to model this time series. Okay, because after leg 2, there is a cutoff in terms of ACF. Okay, this is the typical characteristics of MA model. Okay. All right, so this okay, so this is activity 4.3. Do you have any questions? Are you okay with the plot and ACF, PSF interpretation? Okay, great. So yeah, we are on the same page. Okay, so let's continue. So Corey log. Let's look at the ACF and PSF of MA model. Okay, of MA model, you can see the ACF of MA model with order Q, MAQ model, and after the Q legs, okay, and then all ACFs theoretically there will be 0. Okay, theoretically there will be 0, and so there is a sudden cutoff at like Q. And so we can use MIQ model. Later we will say what is the MIQ model, okay, to model this time series, okay. So this is called a clear cutoff after leg 1. You can see this is leg 1, and then all the other, this is theoretical, okay, theoretically all the ACF for MA1 model after leg 1, that should be 0, okay, all those ACF should be 0. And but the PSF may not all 0, so that decreases maybe exponentially, you can say, right? But they are not all 0, you can see, right? So this is a typical characteristic of MA1 model. Okay. So what is the MMQ model? So this is the model. Okay, this is the MAQ model. YT your time series, mu is your mean, and epsilon t is your random terms in period t, and then all the other error terms in previous period. Okay, so you can say this is it is a linear regression, right, of the random or errors in the previous period. Okay. And okay, Okay, we discussed what is the white noise, right? White noise refers to IID, normally distributed random terms. Okay, and uh, here, yeah, this is IID, right? The mean is zero and the variance is constant but unknown. So we need to estimate this actually from when you estimate the MI1 model, especially you estimate those parameters. And so you can see they are normally distributed with a constant variance and mean zero, and there are no correlations among the residual or those random noise or random terms, right? So they are independent from each other. And so this is the MMQ model. When you estimate this, and this mu you need to estimate if it is not centralized series, and you need to estimate all the coefficient and also this sigma, the variance of the random term. Okay, sigma square. Okay, so this is the MAQ model. Okay, MAQ model. Okay. Now let's look at a specific MA, the most simplest MAQ model, MA1 process. Okay, M1 process according to the definition of the MAQ model. So mean plus epsilon t minus negative sigma theta 1 times sigma t minus 1. Okay, so you need to estimate the mean, you need to estimate the variance, you need to estimate this theta 1. Okay, remember we use negative minus theta 1, okay, in MAQ model, M1. So the mean, you can see you take a mean from the both side because we assume this epsilon t is white noise, right? White noise, so mean zero, constant variance, and so you take expectation, so the mean is mu, right? Means mu. And the variance, okay, you take variance because sigma t and sigma t minus 1, they are independent. So the variance will be this sigma square times 1 plus theta 1 square. Okay, so this is the variance. And the autocorrelation function, ACF, and you can see this is a theoretical LCF, right? Theoretical LCF for leg 1, okay, leg 1, this is ACF, but for all the other legs bigger than 1, and all ACF should be 0, right? Because for this YT only depends on epsilon t and epsilon t minus 1, right? And for example, yt minus or yt minus or yt plus 2, let's see, yt plus 2 will depend on epsilon t plus 2 and epsilon t plus 1, right? Because they are independent, right? You can see epsilon t minus 1, t plus 1, epsilon t plus 2 are independent from epsilon t and epsilon t minus 1. So definitely they have no correlation, right? So for any leg bigger than 2, bigger than 1, so the ACF will be 0. Okay, so this is the MA1 process. So this actually gives us a hint, right? If you look at your time series, and if the autocorrelation has cut off after leg 1, right? So we can consider MI1 process of to model the time series. Okay. Okay. So let's look at this. Just tell me what is mu, what is theta 1 in this activity. It should be very straightforward, right? What is mu in this MI1 process? What is theta 1? The coefficient. Yeah, are you all with me? Are we on the same page? So remember, what is the definition of MAQ model? Can you tell me what is mu here? What is theta 1 in this model? All right, Louis, you mentioned mu equal to 17.8 and theta 1 equal to 0.25. Correct. Okay. And Kenwin, remember what is our definition of MAQ model? Okay, we use minus theta 1 times epsilon 1, t minus 1, theta 2, minus theta 2 times epsilon t minus 2. Okay, so this theta will be 0.25. Okay, yeah. Remember, do be careful because once you look at the output from your R, you need to write down the model, right? You look at the output, you need to write down the model. So remember, this is theta 1, not a negative theta 0.25. Okay, yeah. All right, so it's quite straightforward, right? Yeah, so just remember the definition of MAQ model. Okay. So we will use this TS ARIMA function, right, to fit the MM model on the time series. All right. So the order so refer to this ARIMA because later we will say ARIMA PDQ model. This is the P order for the AR process. This refers to the difference order. This refers to the MA order. Okay. So there are three arguments, right? You need to specify. So we can use MA1 model to model because you look at the ACF. So the ACF has cut off after leg 1, right? After leg 1, so you can consider use MA1 model to fit the time series. All right, so let's go back. So we will use MA1 to model MA1 MA maybe simple to TS ARIMA, okay, function. And your data MA1 series and order, okay, order equals C001, okay. So this is we will use MA1 model. So let's look at the MA1 model, okay? Fitted MA1 model for this time series. Okay. Here you can see this is MA1 model, and this is a coefficient of that MA1 term. This intercept actually refers to that mu, okay? And so you can write down this maybe if you use YT, right? YT will equal to this 11.9934 minus negative 0.8198 epsilon t minus 1. Of course, you also need to have epsilon t. Okay, so this is your fitted model. Okay. And here, so let's look at once you fit the model, you will have residuals, right? Residuals. So let's look at the residuals. Okay, we use TX Explore MA1 MA, this model residuals. Okay. And let's look at the ACF and the PACF for the residuals, okay? Maybe 20 or 30. So this is a residual, right? Line plot of your residual after fitting MA1 model for this time series. And this is a line plot of the residuals and histogram, box plot, QQ plot, ACF, right? ACF of the residuals, right? Because ACF for leg 0 always equal to 1 for any, right? Any time series, okay? Now, after leg 1, you can see leg 0, you can see all the ACFs, you will see they are, you can say they are 0, right? Because they are within this blue area or within 2 standard deviation from 0, okay? And if you look at the PACF, let's look at the PACF, okay? PACF also. And this ACF means, look at the ACF plot, that means there are no correlation, right? Between the residuals, right? The residuals are, you can say, independent. So because the ICF are 0, right? From leg 1 to even up to leg 30, okay? And the PSF, again, you can see no value is significant from 0, right? So this is a PSF. And if you look at the t-test, the location test, and so mean 0, so we will not reject that because p-value is bigger than 0.05. And a normality test, right? You look at the Shapiro-Wilk test, so p-value is also bigger than 0.05. So we will not reject the normal distribution hypothesis. So they are normally distributed with mean 0. And if you look at the independence test, and so you will not reject the independence test, right? So they are, you can see, they are independent. So those residuals that follow normal distribution with mean 0 and also independent, okay? And the residual, if you look at the stationarity test, okay, the residual seems right. This I look at this, well, maybe something wrong. Okay, the p-value is always 0.01. Okay, seems okay. For many cases. Okay. So here you may say safely say this MM1 model fits this time series quite okay, right? This MA1 model. And of course, you can fit MA2. Okay, so let's look at MA2. Okay, so maybe we fit MA2 model. Okay, MA2, that time series. Okay, TS RIMA MA2 series. Right? It's a big series order. Okay. 002, okay, MA2 process for the second time series, okay, and you can print MA2, okay. So this is the second time series, you fit it as MA2 process, right? If you look at the p-value, they are all significant. MA1, MA2 are very significant, right? P-value. And also the intercept, which is the mean, is also significant, right? And okay, and you, of course you can look at the residuals, okay? TS explore. Okay, something residuals. Okay, okay. All right, so you can see This is a line plot. You look at the line plot, QQ plot, and yeah, you look at SAF of the residuals, right? And all the SAFs for leg from leg 1 to leg 30 are 0. And you look at the PSAF, and from leg 1 to leg 30, and PSAF are 0. And so it seems they have no correlation. The residuals have no correlation. The t-test, okay, t-test. So they are the mean is 0, and they are normally distributed, and they are not correlated. Okay, yeah. So here MA2 can fit the series quite well. Okay. Can you all follow me? Okay, great. Okay. Okay, great. Okay, so basically, yeah, we fit this two-time series with MA1 model and MA2 model, right? So here you can see the coefficient, the MA1 terms are very significant. The intercept also significant. So the model is this mean plus epsilon t minus negative 0.8198, right? This theta 1, right? Theta 1 equals negative 0.8198 times this epsilon t minus 1, okay? Yeah. All right, so yeah, you can also look at the AIC information from the output, and this is a sigma estimate, right? This is a variance of your white noise, okay? The variance of your white noise and the log likelihood, okay? So these are the output. All right, so let's continue. So evaluate, we just perform this, right? So you look at the residuals, okay? And then here you can see this, remember when you finish the model part, right? You need to perform the analysis on residuals, right? The residuals, right? You look, first, of course, you need to look at the p-value of your model, right? The p-value of your model, right? The MA term or MA1, MA2, and the intercept term, right? Whether they are significant, right? And usually we use 0.05, right, to indicate the significant level, okay? And the p-value should be smaller than this significant level. And we perform the residual analysis, look at the ACF and PSAF, right? ACF here after leg 0 or from leg 1 to leg this 24, right? They are 0, okay? And then PSAF are 0, so there are no correlation between the residuals, okay? So residuals are independent, right? No correlation, okay? And then you check the normality, right? Normality of residuals using QQ plot or this Shapiro or Wilk test, right? So you will not reject the normality test, right? That they are so normally distributed, right? And then we look at the independence of the residuals, basically similar to SAF, PSAF. So Aljun box test. So you will not reject this, okay? And then you look at the plot, line plot of your residual. Remember, you look at you because you are performing a residual analysis, right? No obvious pattern, right? From these residuals. Okay, that seems a variance should be seems constant. Okay, homogeneous. Okay. And okay, you can of course summarize the model, use summary. Okay, use summary function. I will not demonstrate this, it's quite straightforward. Or you use a TS model evaluate, right? TS model evaluate function to evaluate the model you just fit. Okay. And you look at the AIC information, AIC corrected BIC information. So this actually will be a guide when you have different models, right? You select which model is better. So we look at the AIC, BIC, the model with the lowest AIC and BIC will be selected. Okay, you may have, for example, for this model, you might have MA1 to model the time series. You might consider MA2, right? Or you might use ARP model to consider. So eventually you will compare which model is better. You look at the AIC information, BIC information to select, all right? Okay, so this is the residual analysis of model, fit the model, right? Okay. So this activity, right? We look at the series. Oh, we finished, right? We just finished, okay? We finished this, so let's continue, okay? So we fit the this series with MA2 model, right? MA2. Okay, now we fit the time series with MA model. Now we use forecast, how to forecast, one step ahead forecast, right? This is a one step ahead forecast, right? Because here, remember your model YT plus 1, right? Equals your mu, right? Plus epsilon, yeah, I think here, yeah, we have plus epsilon t minus plus 1 minus theta 1 epsilon t, right? This is in period t plus 1, you will have this. But in you're studying at a period t, and this is not happen, right? You don't know this. So this will be mean 0, right? Mean 0 and variance sigma square. So you will just have this. So we get this error term. For example, once you have yt plus 1, and this is your estimated yt plus 1. And here, because this is y, this because you don't have epsilon t plus 1, so your estimated will be this number, right? Your estimated or your forecast value at t plus 1 will be mu minus theta 1 epsilon t, right? Because epsilon t is observable, right? You have yt, you have yt hat, right? Yt hat from is based on the model, right? You just fit the model, you have yt hat, okay? And epsilon t will be yt minus yt hat, okay? So, and then let's look at, suppose you have yt plus 1 hat, and you have observed yt plus 1, and then this will be the realized epsilon t plus 1, right? Because yt plus 1 hat is based on your model, and yt plus 1 is your observation, and then epsilon t will be a realized random term or white noise, okay? And here, yeah, this is we just explain. And so your one step ahead forecast will be yt plus 1 hat equals mu minus theta 1 times epsilon t, right? And epsilon t is your observation based on your yt and your forecast yt hat. Okay, so this is a one step ahead forecast. Okay. All right, so we don't have time to have a break. If you want to have a break, you just go ahead. Okay, I will continue because we have, I think, a lot of things to cover, right? Okay, so any future period, okay, let's look at this is a error term in t plus h, right? Period t plus h. So h that bigger than 1. So this is your, but in all t plus h that bigger than 1, we don't have the actual observation, right? So we need to use a forecasted value to represent that. And then this is the forecasted value minus forecasted value. So all will be 0, right? So for any future periods, epsilon t plus h will be 0. And then this will give us this very interesting result. That means any forecast value for period bigger than 1, and actually it is equals to the mean of the time series for MI1 process. Okay, for MI1 process. And so let's summarize this. So basically you can see for any h is bigger than 1, okay, bigger than 1, so the forecast value is always the mean of the series, okay, your original series, stationary series. And of course, this is your h less or equal to 1, including h less than equal to 0, is your original time series, and then you fit the model, and then you know the so-called the white noise, the term. Okay. Okay, yeah, so of course, when we do forecast, we have so-called confidence intervals, right? We have confidence intervals. And this usually we will have, for example, 100% times 1 plus alpha percent confidence interval. For example, if alpha equal to 0.05, this will be 95% confidence interval, okay? So this confidence interval of your forecast, a forecast value, right, will be an interval plus this is your mean of your forecast, and this is the error term. Okay, so this z of, sometimes we use z of alpha divided by 2, and some textbook or some textbook will use z of 1 plus 1 alpha divided by 2. Basically, it is a normal distribution, right? Zero with zero standard normal distribution, right? And this value, right? This return in terms of half alpha divided by 2. Okay, the probability of this area. So this will be this value. Okay, the critical z value. Okay. And for alpha equal to 0.05, so this z value will be 1.96. If alpha equals 0.1, okay, 0.1, so this critical value will be 1.64. Okay, if alpha is 0.01, and this critical value will be 2.56. Okay, so this is from the basic statistics. All right, so this is a confidence interval, right? When you do a forecast, you will have a confidence interval, and usually you don't need to care about what is the standard error, and I will estimate that for you. And then you just get the confidence interval, and here how we calculate the confidence interval. So the estimate or this forecast plus minus those z value times this standard error. So basically this you can see z value for 95% confidence interval, z value is 1.96 standard normal distribution. Okay, 1.96, and times this standard error, so this will be the range of the half of the range of the confidence interval. So the mean, the estimated value minus plus the range will give you the 95% confidence interval of your forecast. Okay. So you can use the TS forecast function, right, to do the forecast in R in this package. Okay. And this is your model. This is your 12 period ahead. Suppose you want to forecast the next 12 months. Okay. And then you can plot it. You can plot the forecast value. Okay. So it's quite let us demonstrate this. So TS forecast, okay, and your suppose your MA1 model, and you want to forecast the next 2 period, and let's and you just want to plot the forecast value. Okay, so this is what we will have. Okay. All right, so it's yeah, so I will not yeah, let's go back. Okay, let's go back. All right, so calculate 12 months forecast series in MA2, right? General plot. So it's quite straightforward, right? So you can just go back to get this forecast. So let me do it. TS forecast, MA2, MA model. Oh, So 12 period, let's just plot the forecasted value. Yeah, so this is what we will have, right? So this is activity, all right? Okay. I'm fast now because I try to maybe complete the content. Then we will do a review maybe in seminar 5. Okay, so let's complete the content in this seminar. So MM model, okay. So basically you need to know the past white noise, right? You based on the past white noise, you generate you feed the data, right? And the white noise will be once you fit the MM model, you do a residual analysis, right? The white noise should be IID normally distributed with mean zero and constant variance, okay? So MM model are stationary in both the mean and the variance because we know the mean is a constant and the variance depends on how many the MA terms, right, in your model. Okay, so they're also a constant. So MA model is always stationary. Okay. When we look at the SAF of the stationary time series, and if the SAF have a cutoff after period lag Q, then but the PSF decays exponentially with increasing lag. So means there are no cutoff in terms of PSF. So we can consider using MAQ model to fit your time series. Okay, your stationary time series. If your forecasting period exceeds this order Q, that means the forecast value will be always the series mean. Okay, because after the model Q, you don't know the white noise, right, from your data. So you have to replace those with zero, mean zero. So all the forecast value after lag Q or after period Q or ahead will be the series mean. Okay. So we need to estimate the past white noise, right, to determine the forecasted future values. So this is why we don't have we can only forecast the period of the same order of MAQ model, right? After Q period, so all the forecast will be the series mean. All right, so that is the MA model. Remember, when you look at the ACF and PSF, if there is a cutoff in terms of ACF, while there are no cutoff in terms of PSF, you will consider MA model. Okay, now let's look at maybe another seems interesting model. Means when you look at the ACF, there are no cutoff. Okay, but if you look at the PSF, there is a cutoff. Then you can consider this AR model, autoregressive model. Okay, so this is example. I think, for example, based on AR model, and you have sales, you have forecast, and then you look at the error, and then you may have forecast in period 2, which is 104, but the actual is 96. You have error. Okay, and maybe the forecast in period 3 based on the past value, past sales values, and based on some of the maybe errors, and you have forecast and you have actual value and you have error and so on and so forth. Okay, so we say AR or MM model cannot simply be applied to any time series for forecasting. Why? Unless your time series is stationary. Okay, the series must be an AR process which fulfills certain characteristics. Means there must be stationary, and then after you fit the AR model, the residuals are white noise. Okay, otherwise you cannot directly apply those models in your forecast. Okay. Okay, so AR series 1, AR series 2, so look at the ACF, PSEF, something. So I will do it quickly. So we import the data into R. AR1 read the data. What is AR? AR series. So series 1 to CSV. Okay. Okay, so this is the time series, and I will continue with date, change the date, AR1. And let's make it a time series. Okay. Okay, yeah. So this is the time series we will have, and let's similar AR2. Okay, AR2. The other time series we import into. Okay. Okay, this is two data set we import to R. So if you look at let's look at the ACF or PSF. Okay. Let's say 30. Okay, so this you will look at the line plot of this time series distribution and this series, right? And you look at the ACF, you can see the ACF actually decreases. You can say exponentially, but there is no clear cut off, right? And if you look at the PICF, okay, PICF after leg one, right? After leg one, all the other, but some of this maybe leg 17 maybe is a little bigger than zero, right? Different from zero. But here, if you look at this PSF, it seems there is a cutoff. Okay, so we can consider model this as a AR1 process. Okay, so we let's similarly let's look maybe we model this. Okay, AR1 AR process TS ARIMA order. Okay, 100. Okay, so this will be the AR1 process to model this time series. And let's look at this model. Okay, so this is the model. If you look at AR1, this p-value is significant, right? The intercept. But here you need to be very careful, okay? Very careful. Here we have an intercept. And here we have a constant estimate. Okay, this actually refers to that constant estimate, while this actually refers to the mean. Okay, this actually refers to the mean of the time series, and this refers to the constant in your AR model. okay, ARP model, all right? So this you must be very careful, okay? And similarly, you can, well, let's look at AR2, okay? Uh, AR2 time series. This is this series. Oh, explore, okay. Yeah, so if you look at this time series, there seems volatility clustering, right? Volatility clustering, and of this time series, and let's go to this. Okay, the ACF. You can see ACF decreases, yes, exponentially, and but not but don't have a cutoff, right? ACF plot. But if you look at the PSF, okay, PSF leg 1, leg 2, right? After leg 2, there seems a cutoff. So we may consider AR2 process, right? AR2 process. So let's model this as AR2 process, okay? Okay, so this is AR2 process, and you can see that both terms are significant. AR2 process and intercept is also significant, and pay attention to this constant estimate. This refers to the constant in your model. Okay, this refers to the mean of the time series. Okay. All right, so it's quite so let me go back to the slides. All right, yeah. Okay, so this is, you can see ACF and PSCF, right? And so if for AR process, so there is a cutoff after leg, after a certain leg, you will consider use AR model, right, to model your time series, okay? So this is AR1 process, and typically you can see this is decrease exponentially, but in a damped manner, like a sinusoid something, right, pattern. And the PSCF will be a cutoff. There is a cutoff, okay, after leg 1. So this is the AR model, okay, ARP model. So you can see it's a regression among its past P period values, right? This delta is referred to the constant in your model, okay? And not like the MM model, this constant refers to the mean for MM model, okay? But here, this is not a mean, okay? And this is the ARP model, okay? So here, once you fit the ARP model, you do a residual analysis based on the residuals and check whether residuals are white noise. If the residuals are white noise, okay, your job is done, right? You finish, extract all the information from the time series. So this is the AR1 process. You can see this is the model, AR1 process. This is the mean, right? Delta minus divided by 1 minus phase 1. So, and the variance, right? And here, in order to be stationary, right, we need AR process to be stationary, means we must ensure the absolute value of this phase 1 must be less than 1. Otherwise, you can see you don't have variance, and then you will have no so-called this and if you simulate this process, you will have explosion, right? If the absolute value of phase 1 is bigger than 1, okay? And you can see autocorrelation equal to phase 1 times k. So there are no cutoff for ACF for ARP process. Okay. Here, the stationary, if you look at this, right, for AR1 process, we say if this if coefficient, the absolute value is less than 1, then you are stationary. The process will be stationary, okay? And you fit the, yeah, we just finish this, right? We use a TS remark function to fit the AR process. So you look at the SAF, PSAF. If SAF have no cutoff, but your PSAF has cutoff, you will consider this AR process, okay? And remember here, refer to the constant in your model, right? Refer to the constant in your model. While you can get the mean, this is the mean of your time series. Okay, this is the mean, which is 8.0311. Okay. And so you look at the output, you should be able to write down the AR model, okay, ARP model from the output. Okay, so we actually finished, right? Finish this. But of course, we need to do a so-called residual analysis. Okay, residual analysis for the AR model after you feed the AR model. All right, so this is forecasting. Okay, forecasting basically one period had forecast, and so you know this because you know YT. And but let's look at the 2 period had forecast, and then YT plus 1 you will substitute this here, right? And then you can see this will be this guy, and then YT Y you want to forecast the H period ahead, and then you will continue with this, you will get this formula. And because phi 1 absolute value is less than 1, if H becomes bigger, for example, infinity, so this will be 0, and this will be 0, right? Because phi 1 to the power of H will be 0. So eventually you can see the forecast will be converged to the mean, right? Delta divided by 1 minus phi 1. Okay, so this the series mean will, the forecast value will converge to a series mean. Okay, you can also get the confidence interval of your forecast. Okay, forecast. So similarly, right? R will estimate the standard error, and you just plug in the formula for 95% confidence interval. The z value, critical z value is 1.96, and then you use this 1.96 times this standard error, you get the margin, right? Minus the margin plus the margin, you will get the confidence interval, upper bound and lower bound. Okay, so this is the confidence interval. Okay, so similarly, you can use the TS forecast. Okay, TS forecast, right, to forecast the value after you fit the model, right? Okay, so I will not demonstrate this because it's quite straightforward, right? Like what we did for MA model. Okay, so yeah, do a quick summary, right? Because it's almost 10 p.m. And so the autoregressive model, okay, autoregressive model, basically you can see it's based on, it's a regression, right? Regression based on its past values, okay, in past period. And for, if you look at the ACF and PSAF, for if PSAF have cut off after certain lag, you will consider AR process. Okay, and if you yeah, the ACF is decays exponentially, no cutoff, but ACF has cutoff, you will consider ARP process. Okay, and is stationary means those coefficient enable you have constant mean and variance, right? So for AR1 process is quite trivial, right? If the absolute value of the coefficient is less than 1, your AR1 process is stationary. But for AR2, AR3, even more, and you may have other conditions, okay? And okay, so the forecast process AR forecast of ARP process depends on observation of forecast value of most recent period. Okay, yeah. So yeah, so this is for AR process. Basically, for AR process, we need to look at the stationary of the model. While for MA process, remember MA process is always stationary because you have constant mean and variance, right? But MA process, we will look at its so-called invertibility because the ACF and PSF will not uniquely determine the coefficient of MA model. So, but we will always look for an MA model which is invertible. Invertible means the MA model can be converted to a infinitely, AR process. Okay, MA model can be transformed into an infinite AR process. It means invertibility. Okay, so I think we have videos in Canvas L01 module. You should watch the video, right, to understand what do we mean by stationarity for the AR process and the invertibility of MA process. Okay, yeah. So we are quite rushed, right, for today because we will go through this, maybe do a quick review in seminar 5. Do you have any questions? Do you have any questions regarding the AR model, ML model, right? I think if you understand ACF, PSF, right? So if you look at ACF, PSF, if ACF has cut off, while PSF has no cut off, you consider ML model, right? And if you have ACF no cut off, but PSF has cut off, you consider AR model, okay? But remember, we focus on stationary time series. Your time series must be stationary so that you can apply AR model, ML model. Otherwise, you will have problems. So you need to remove the trend. You need to remove seasonality, right? You need to remove cycles and make the using difference or use log transformation, right? So you have a stationary time series, and then you use AR model, MA model, and then to fit the time series. And then you do a residual analysis to check whether the fitted model is good or not, right? If the residuals of your fitted model, right, the residuals are white noise, then your job is perfect, right? You extract all information from the time series. If the residuals are not white noise, that means you need to consider other models, right, to continue fit the time series. All right. Okay, so this is all for today. And if you have any questions, I'll be here for a few minutes and let me know. We can discuss. Okay, if you don't have any questions, you can leave the meeting and enjoy your evening. Okay, I look forward to see you in seminar 5. And remember, you need to submit your GBA report by this Sunday, right? Do not do that at the last minute, okay? Upload your GBA report at least a few hours before the deadline in order to avoid any, unfavorable circumstances, okay? Yeah. This is all for today. Do you have any questions? You all are very quiet, okay? Okay, great. Not for the moment, okay? Sure. And if you have any questions, let me know. Send me email, and or we can have online meeting or chat something. Okay. Uh, 智慧 Eileen, right? You know, GBA, one person will submit. Yes, yes, yes. Only one person. Okay, the leader. Okay, you can consider as a leader. A leader submitted the GBA report to Canvas. Our T group remember, do not submit wrongly, okay? Do not submit your GPA report to other courses, okay? Otherwise, you need to appeal and you need to pay sometimes, okay? You need to pay.